Hello, my name is from Group B1, and today I'm going to talk to you about how to handle your flow visualization activities. Now, the first thing you need to do is to wear proper PPE attire. So, first you wear a lab coat to protect your inner clothing from stains, safety goggles to cover your eyes, and gloves when handling the dye to avoid skin irritation. Now, let's check that the workpiece is dry and free from water spills. So, like there are some water spills here. So in this case, you need to have a paper towel or a mop nearby to prevent slipping or damaging nearby equipment. Before you start the flow system and during the flow, like during operating the flow system, you must inspect all tubing, connections, and valves to be completely free of cuts or damages of any kind. So that way leaks or spills will not happen, especially like dye spills and leaks, because that would be a problem. It would cause stains and contaminations. And especially when it comes to dye, you have to handle the dye with care. You use a funnel or a pipette to refill the dye here. You pour this inside without spilling it outside. And if there's some dye stains around here, you have to make sure to wipe it up completely. I'll say it again, be sure to avoid skin contact with the dye, because it might cause skin irritations.
This approach here is HTML15 Flow Visualization units. From the beginning, you can see this is the base of unit. We have two handles at two sides of the base. From the beginning, this is the water injection, and this is where we put ink. The ink will be injected into the hole from here. This is the water inlet. After the water will be injected into the flow chamber over here, and on top of it, we have the glass panel on the top of flow chamber to observe the flow. The flow goes through the chamber, and over here, this is the water discharge. The wastewater will go out from here.
Hello, my name is Cornelius from Group and now I'm going to explain how to conduct the experiment using the fluid flow components. So first things first, we have to open the water supply. And next is to prepare the dye water. And as you can see, we've already done that. And it will look like this. The next step is to put the specimen inside the fluid flow chamber. So for this experiment, we will be using this car specimen. First is to open the chamber. And we shall put this car here. And make sure there's no air bubbles in between the car and the fluid flow chamber. Lock the chamber. Make sure it's locked. turn on the water supply valve. So we'll start with A. We slightly open the valve and let the water run through here. And next is to put the dye water inside the tank. After that is done, we will open, as you can see, the water as the dye water started to move. So now we will as you can see, we have locked the fluid flow chamber with the specimen inside. So next we will slightly open the water supply valve. And next we will open this. And as you can see, the color has started to run, and we will refill again. As you can see, the dye water has run. We'll open the valve, these two valves, valve B and C of the water supply valve. And as you can see that you can clearly see the dye water started to flow inside the fluid flow chamber, and we can clearly see the
My name is
fluid flow
Lotus
visualization.
and we're talking about the
specimen
result.
of the car
So
inside.
for this experiment, the main objective of our result section is to measure and record the flow characteristic of water through 3 different outlet shapes. The primary data collected was the time taken for 2 liters of water to discharge of each shape. So we tested 3 different shapes: shape A, shape B and shape C. For each of these, we measure how long it took for the water to reach the 2 liter mark using a stopwatch. The recorded time were 96 seconds for shape A, 83 seconds for shape B, 50 seconds for shape C. From this data, we calculated 2 important flow parameters, which is velocity and the Reynolds number. The velocity is calculated using the formula U equal to volume over time, where the volume is 2 liters. So for each shape, the velocity for shape A is 0.0208 meter cube per second, shape B 0.0241 meter cube per second, and shape C 0.04 meter cube per second. Then we calculated the Reynolds number to understand the type of flow, whether it's laminar or turbulence. The formula used is RE equal to density multiplied by velocity over dynamic viscosity, which is 1.0 times 10 power negative 3 Pascal second. So the Reynolds numbers are, for shape A is 20.8, shape B 24.1 and shape C 40. Since the critical number of Reynolds number for transition from laminar to turbulent flow in pipe-like system is typically around 2000, all 3 of our shape produce Reynolds numbers well below the threshold. This indicates that flow in all cases is laminar. However, if you compare between them, shape C with the highest Reynolds number of 40 is the closest to transitioning and has the most unstable or active flow, while shape A is the most stable and clearly laminar. This measure and calculated result are important for analyzing the influence of outlet geometry on fluid velocity and flow characteristic. That's it.
Hi, my name is Divish. In the result, the Reynolds number for each scenario are 0.0208, 0.0241 and 0.04. From the straight line image, shapes A and B shows flow closely following the droplets, indicating laminar behavior, while shape C shows a large low pressure wave, suggesting potential turbulence. Thus, Higher Reynolds numbers are associated with increased likelihood of turbulence flow, while lower values suggest more laminar flow.